Hello again, my dear students. Now this is part number 2 with our amplitude modulation lecture. If you remember, in the first part of our lecture, we deal with the basic definition of amplitude modulation. We understand the concept of the modulation index, or the depth of modulation, and these DC offset added in order to overcome what's called the phase overlapping. And then we reach what's called the general definition, or the general mathematical expression for the modulated signal with 1 plus k m of t multiplied by the carrier signal. Now, in the second part of this lecture, we are going to focus on the reverse process, which is the demodulation process. How we can re-extract the message from the S of t, from the modulated signal. So let's now share my presentation slides and start our second part. Okay, perfect. I believe now you can see my presentation slides. This is lecture number 3 with amplitude modulation. Now we are in part number 2. I have just to start operating my laser pointer and start this part. Okay, perfect. Let's go quickly onto the end of part number 1, where we have a general definition for the modulated signal S of t in terms of this block diagram using a modulation index k and a DC offset. And we reach the general expression for the modulated signal, my dear students, and we also understand what's called the modulation depths, and finally we demonstrate the frequency domain of the modulated signal, where we distinguish our AM into 4 main modulation techniques. The first was what's called the double-sided AM modulation, or double sideband DSP AM. In the DSP AM, we have 2 redundant versions of the signal in addition to the carrier. Also, we have what's called the DSP suppressed carrier, or the double-sided band suppressed carrier, when you kick out this carrier from the equation, and then you have just the message. And also, we have what's called the single-sided band, where you have only one band of the signal. And finally, something out of scope, which is the vestigial sideband, or the VSP. Now, what about the demodulation process? Again, the definition of the demodulation process is very, very, very easy. It's just the reverse process of the modulation. So in the modulation process, some slides ago, we have understand that it's a process of transferring a baseband signal into a passband signal. Now, in the receiver side, you are willing to return back this passband signal to be a baseband signal. So this is simply the concept or the idea of the demodulator. What we are going now to do is that we are going to illustrate 2 different types of demodulators, and we'll start to think about the concepts beyond each of them, and also the advantages and the disadvantages of each of them. So let's start with the first demodulator, which calls the square law demodulator. Let's examine now the concept. Here we have an input signal. Then we have something that's multiplied the signal by itself, so it's some sort of squaring. After that, we have a low-pass filter, and then we have some sort of square rooting. And finally, we get the output. So let's start now to examine the mathematical model beyond this square law demodulator. Okay, so now let's turn the camera, please. Okay, I think now you can easily see my whiteboard. I believe so. So that's perfect, and let's start the process. So first, let me replot this block diagram. Again, we have here something to make a square. a low pass filter, and finally something to have the square root, where here you have the output. So what is the input? The input is basically this S of t. So what is the S of t? Very easy. S of t is AC times 1 plus k m of t cosine 2 pi fct. Now, as you can see from this block diagram, that the first step is simply that you square the signal, or in another way, you multiply the signal by itself. So what we are going to do here is to have s square of t. So now this s square of t is simply looks like this. It's ac square 1 plus k m of t all square, and then we have cosine square 2 pi fct. This is very simple like that. Here there is no problem actually, this is just a constant square. So this is again equal ac square. And now what about this? Here you have three messages actually. You have 1 plus 2 k m of t plus m k square m square of t. So this is the output. And finally, you have a cosine square. So you have to return back to the mathematics, your mathematics classes, to remember how you can deal with this cosine square equation or cosine square function. Okay, if you return back to your mathematics classes, you will know that cosine square x is equals to half 1 plus cosine 2x. One of the famous trigonometrical functions. So in a very simple manner, you can continue writing this equation in the form that it's half 1 plus cosine 4 by fct. So now all these bracket is now multiplied by 1 or multiplied by this. So let me continue. So you will get something like that. S square of t equal ac square over 2. 1 plus 4, sorry, not 4, yeah, 1 plus 2, I'm sorry, 1 plus 2 k square m square t. No, I'm sorry. I am sorry. Okay, so s square of t equal ac square over 2, 1 plus 2 k m of t plus k square m square of t. This is the first bracket, and then all these plus. Now I'm just multiplying this term by 1, and I have here. Now I will multiply this term by the cosine. Just to avoid any misunderstanding. So now I will multiply this term by cosine. So we have ac square over 2, again the same bracket, 1 plus 2 k m of t plus k square m square of t multiplied by cosine 4 by fct. This is simply the s of t. Here you have to stop mathematics and start thinking. It seems that you have two components. The first is function in MFT and M square T, which is basically a baseband signal, if you take care. No high frequency component is. And the second is at F frequency equals to FC. So here, after squaring the signal, you end up with two terms. The first is a baseband term, and the second is a double carrier frequency term. That's why, if you return back to the block diagram, either here in the paper or in the slides, you will find that we have such a low-pass filter. So here, as a system engineer, if I told you what is the specs of this low-pass filter, what do you need from this low-pass filter? Simply, you need to suppress the high-frequency component and to pass the baseband signal. So the main restriction here is your cutoff frequency should be smaller than FC, 2FC. So that if your cutoff frequency is smaller than 2FC, then basically what you are going to do is that you will reject this high frequency component and you will only pass this component, which is simply as follows. So after passing this S square of T over a low pass filter with F cutoff smaller than 2 FC, what we will get is something like that. Let's call it, for example, anything. Let's call it S dash of T. So this S dash of T is S square of T after passing the low pass filter is equals to AC squared over 2 1 plus 2 K M of T plus K squared M square T. Finally, you have this very simple square root block diagram. So the output of this square root will be simply the square root of the input is the output. So what I'm going to do is just to make a square root of this. So you will have S, let's make it S double dash of T, for example, which is the final output, equals to AC over root 2 over 1 plus M of T times K, of course. So as you can see, now I have the message, but actually it's not only the message. I have the message, this multiplied by a factor called K, which is somehow a modulation factor I already adjusted in the modulator, if you remember, and also multiplied by another factor, which is AC over root 2, again another constant, and DC shifted somehow with a DC shifting value is AC over root 2. But all this stuff can be easily kicked out. For example, if you would like to kick out the DC value, you can just put the signal over a capacitor, and that's all. And using an amplifier or an attenuator, you can attenuate the amplitude of your message. The technical content is here, is in M of T, and you still have this technical content through the M of T signal. So as you can see from this diagram, let me now return back to my slides, please. As you can see from this diagram, my dear students, you're now able to rebuild or retake or reconstruct the message, which is the M of T message again after this very simple block diagram. So this is one of the methods used for extracting or for demodulating the AM signal. Let's take another example. Okay, let's do the next example. The next one is what's called the coherent demodulator. Very simple. We just have a mixer again, multiplying by the carrier and the low-pass filter. Let's see what will happen. Again, let's turn back to our whiteboard. So what we have now is as follows. Our S of t signal is passing through a mixer with cosine 2 pi fct, and then we have a low-pass filter. As you can see, in such examples or in such systems, maybe one of my final exam question is design an appropriate low-pass filter, as we already did in our first example. So it's very simple. Let's do it. Now, S of t is AC 1 plus k m of t times cosine 2 pi fct. Okay, let's call this S dash of t after the mixer. So simply S dash of t is just the same S of t multiplied by another cosine 2 pi fct. Okay, let's see the output. So the output S dash of t is equals to AC 1 plus km of t cosine square 2 pi fct. Perfect, the same. Now you have the same cosine square, which is equals half 1 plus cosine 2x. So this is simply equals to AC 1 plus km of t multiplied by half 1 plus cosine 4 by fct. Perfect. Now you can extract your signal. So this is page number 3. Okay. Now you can extract your signal. So here, S of t equals AC 1 plus km of t cosine, no, there is no cosine, plus AC, here there is over 2, I'm sorry, and here again there is over 2, AC over 2, 1 plus k m of t cosine 4 by fct. Here again, two signals. The first is baseband, the second is at a frequency 2fc. By using a very simple low-pass filter with a cutoff frequency smaller than 2fc, you can suppress the high frequency component, and then you can get easily the AC 1 plus k m of t, which is some sort of the message. Okay, so from the first impression, my dear student, you can say, okay, the second one is much easier than the first one. We don't need this sophisticated block diagrams that makes the square root. It is just a multiplication in high frequency or an RF mixer and a low-pass filter. That's all. That's 100% true. However, let's return to the slides and make a very important discussion regarding these points, my dear student. Okay, so basically, this block diagram is much easier than, the first one, where we have the square low demodulator. However, herein you need what's called a coherent carrier. What I mean by coherent carrier is a signal that is typically equal to the carrier. Equals to the carrier from which perspective, my dear student? Equal to the carrier from the frequency and the phase perspective. The frequency and the phase perspective. This is extremely important and extremely difficult. Herein, I invite you to make two important assumptions. What if the new generated frequency in the receiver side is somehow shifted with respect to the transmitted side? For example, what if the frequency is FC plus delta F, not FC? What will happen? We have to think about it. You have to solve it, as you can see. Let's do another example. What if there is some sort of shift between the phase here and the phase there? So you have cosine omega CT plus phi. What will happen to the receiver signal? Let's imagine the worst case scenario when you have these phases equals to 90. I mean, this cosine can be turned to be a sine or a negative sign. What will happen? Now, this is a problem. Of course, the coherent demodulators is somehow more simple than the coherent modulator, the square wave low demodulator. However, you pay cost. Why I pay cost? Because you have to have a crystal oscillator in the receiver to generate this cosine 2 pi FCT signal. Secondly, you have a problem of asynchronization. Whenever the oscillator in the receiver is not synchronized with the oscillator in the transmitter side. Maybe in our extra sessions, we are going to solve some problem like that. Whenever there is no synchronization between the transmitter and the receiver, either from the frequency perspective or from the phase perspective. And then we will examine the consequences of such asynchronization in the system. Now, by this example, I have terminated my part number 2 of lecture number 3 related to the amplitude modulation. Herein, I have to be clear to tell you that in your exams, I'm not only limited to these 2 block diagrams with a square low demodulator or with the coherent demodulator. Because, as you can see, it is just a mathematical process. So, maybe in your in-class test or in your final exam, you will find a totally new demodulator. What you are going to do is typically what I did, is just to trace this from a mathematical point of view, starting from your S of t till you get the M of t. So, you can easily implement any new demodulator or study, let me say, any new demodulator by just following such a mathematical model. Now, as I told you, this is the termination of part number 2 in our AM or amplitude modulation lecture. In the next week, we will investigate more in the amplitude modulation. We are going to solve some important examples. Again, examples with observations, as we did in the first 2 chapters. So we are going to do some important some important examples related to the AM modulation. Additionally, we are going to investigate more regarding the different types of AM modulation. We will go deeply into the double sideband suppressed carrier. We will have a quick look on the single sideband, and we will not consider the vestigial sideband in this course. Thank you for your concentration, and see you next week with part number 3.